We are on the air. FYI, there's a lot of noise in the beginning of this.
Like, taught my wife saxophone for Christmas. She used to play, and it was really good. And I just talked about it 3 years. I was like, you know, fucking dying. So got her on, and she just like, you know, had to look at a couple of quick refreshers, and she was like on a roll. I'm like, yeah, yeah. Pretty sweet.
Let's set it up.
You do like electronic? Yeah. I paid for a whole studio a long time ago, obviously, but I'm never buying this again because you have to pay for everything else. Yeah, I feel like I'm just using the subscription. Like, in order to get like all the plugins and everything, you'd be looking at a couple grand, maybe even $5. Yeah, that's not happening because I can find my own synthesizers and everything for cheap. Like, I want to have this in my freaking house. Because all the stuff, plugins, but I think that's going to be, you know, a couple of years. Bunch of actually on the list. Those things are so fucking. Then I showed her like a classic one from the 80s. I was like, about this. She was like, okay, that I can let you do. Yeah. But she likes that kind of. So I'm like, we can compromise, maybe. She wants a family. Yeah. But that may or may not ever be happening.
A lot of static in the beginning of this broadcast.
I look up at and started looking at and say
So we're in the game as well. So we just got to focus on a couple examples. And but also talk a little bit about remind you guys where we are. So what we're actually going to do is slight adjustment. We're not going to cover too many examples today, multi-dimensional. So we're going to use actually this lecture to introduce the robotics project. And as you guys also know, you guys have projects and stuff too. And so that's what week 12 is all about. And then we get to week 13, we're going to really kind of focus on robotics. And so we covered a good amount of the theory around what we want to do with robotics on the 3rd. We will probably wrap up what our theory is on the 8th, and want to maybe reserve 410 as a project working. All right, we'll see how far we get. One thing I want to mention to you guys that we're going to need to qualify for the robotics competition during our lab period. So just a quick statement about what that means. You'll have to create a robot, and we're going to do a chase game as far as robotics competition. Okay? So the chase game is an actual competition will be fighting in the lab period. You will be kind of competing one-on-one, single elimination, march madness, kind of tournaments. You're chasing another robot, you're trying to catch it. But before realize what the seedings are, means qualification. Qualification means you do a time trial on the time. Okay, so I'll mention it to say, those guys that want to kind of wrap up a bit amount of this stuff and MechLAB2 early, you can take advantage of this first qualifying period. Okay, the TAs are there, they can log the time for you. All you have to do is just get them to do a stopwatch time trial on the track. The track is just, it's going to be set up in the lab this week. And all it is the secret kiosk with a couple of jobs. All right, so we'll talk in more detail about that. We'll have opportunities to introduce the project on the third. But I would suggest, there's a number of you guys, I know you guys have a lot going on later on in April. I will take advantage of this first qualifying period. So today we're not there yet, we're still focused on uncertainty. And so we're going to do an example on multiple measurement uncertainty today. I'm going to take some time. And we probably will, we're going to have a whole lot, we probably will end up with today. Before we get into the uncertainty, are there any questions about project stuff you guys are working on? I wanted to also mention, and I think this is important because I get employers at least twice, and I've come to you and said, your students really thought that my data acquisition could do an infinite amount of capability. Okay, so I just want to mention it today. What are the limitations of the my data? What are the limitations? Yeah, so quantization there is limited by that, right? So equal scale range on this particular, so let's toss up the data sheet for my data. And actually, you mentioned the full scale range. Go down to this little table here and kind of outline it. Okay. Gives us, this is what we said in our last number. We said it's either 10 to negative 10 or 2 to negative 10. All right, those are the only equal scale ranges my data can do. But it's important for us to also mention that my data is for educational purposes. All right, you can get a pretty inexpensive data that could do negative 1 to 1. It's all based on the device and the hardware, right? So, what is the first thing you might do if you're trying to submit acquisition? The first thing you might do is open up a data sheet like this and look at what the possible equal scale ranges are. That's a limitation. All right. What other limitation do you have? Yeah, that's a big one. Okay, that's a big one. If you look actually, if I scroll up. It gives you maximum sample rate, 200 kilosamples per second. With the MechLAB, if you try to set it higher than 200 kilosamples per second, it will actually default. And that's what all these things kind of make things easy, right? So if you set it to something that's impossible, it's not even going to be here. Right? It's going to default to 200 kilosamples per second. All right. But that's important because we don't want you guys to get your job and have some type of application where you're saying, all right, well, boss, all we have to do is spend $250 to buy my data, because we can just set a million samples per second. And that's how you get fired from a job, right? And then they're going to come look at me like, what's that lady? Talk to this person. So there's limitations, right? So if you want to know the limitation, what we're going to do, we're going to go and grab that data. All right, so here's 200 kilosamples per second. And also, he mentioned, here are the number of bits, right, for A to D. 16 bits is not uncommon, all right? So, actually, it is amount of resolution that is pretty common with analog digital conversion. 16 bits of analog digital converter resolution. All right, if you had an application where you needed more resolution than that, you're going to just pay the price, right? You're going to pay the cost to get better analog digital converter higher than 16 bits. All right, so you're going to pay a premium for more resolution than that. All right, what's the other? What's a huge limitation in the hardware side of the matter? You try to use it. What's the huge limitation? Yeah, and so just want to mention to you guys that again, MechLAB is for educational purposes. What did it give you? It gave you 2 analog inputs. It's pretty common when you're using a like we have one in the lab right now that has 16 analog inputs. And think about the same number of analog outputs. Not to say you don't need that for educational purpose at all, and would you need it at your job? Not necessarily. All right, but that's just one limitation you get with the MechLAB. You guys can think about kind of how you interact with the MechLAB. MechLAB actually is really good when we're providing you guys with very close excitation, which I think is really great. So you can use chips like the iPad that you guys should use for the code. So, but yeah, I just want to mention that because I just want to reiterate that what you're going to do in actuality, you're going to go grab the AFC, you're going to look at what the limitations are. So just kind of expose you guys to what kind of some of the important specs are, so that you guys know what to look for when you're choosing an app system. Another thing that's important about the MechLAB that we have not mentioned yet is that it uses a multiplexer. You might know what a multiplexer is. You might have heard that before. Yeah. Well, so the reason why this system is so inexpensive, and we're able to use it's only like I said, we pay $250 for it. It's because it actually only has the hardware for one analog input. What does it do? A multiplexer allows you to switch and use one set of hardware for multiple inputs. So it's like a switch, right? It'll provide you with, on the hardware side, multiple inputs, but it only uses one set of hardware. Okay, so you can imagine that when we're talking about something like a sampling rate, that's important, okay, because you're actually only using one set of hardware, and it's at 200 kilosamples per second. Once you start using more and more inputs, you only have one set that you're using for everything. All right, so it uses a multiplexer, and the actual circuit diagrams are very front of the MechLAB. It shows you that. All right, so that would be a limitation. All right. I just wanted to mention some of that stuff. We're going to go into the uncertainty that we want to talk about. I have a question about this table. I just want to mention this to you guys. So you guys are looking at TJ in your on your data sheet that's provided. All right, so I'm going to put this in contrast with, you guys remember this table from your MechLAB2. This is a single-sided C table. So the numbers that you get are only considering kind of half of the distribution single-sided. If you remember what you did for MechLAB2, the single-sided distribution is useful for you because you reference everything from 0. So when you did on your conversion to the Z value, you referenced it all from 0. So single-sided Z table is useful. On this table, this is the two-sided student T table. So when we say confidence of 95%, what we're talking about is, if you think about the bell curve, we're talking about 2.5% to the right, 2.5% to the left, that's not covered. All right, so confidence of 90% would mean, if you think about the bell curve, 5% on the right, 5% on the left, that's not covered. All right, so if you look at other references, it might give you a single-sided t-table. Don't get confused by that. But when you're use of the table, as long as you're using the one that's provided by me and you do things the way that we ask you guys to do, you won't make a mistake. I just want to mention that because I did get a question about that. So I'm going to give you guys, I think, a really clear strategy here for most measurement concerns. All right, we're going to go very slowly through this one example. Okay, very slowly. And I want you to ask questions so you all understand. When I give you on the test, it's going to be almost exactly like we're very simple. Okay, so please, we're going to go slowly through this example. And so the reason why we're not going to do a whole ton of different diverse examples of multiple measurement uncertainty, it gets pretty redundant pretty quick. All right. But we're going to cover this one example in pretty good detail. And also it's worth mentioning that one of the assumptions that we're making in almost everything that we're doing in class, and so we're applying the RSS. What's the key assumption that we're making about our problem? Same use, okay, yeah, that's true. But we can't apply a RSS and be valid unless it's one thing is true. That's good. Yeah, not looking for that. I'm looking more so along the lines of even in your calculus class. Let's get back. You found the vector you're applying the form of RSS. All right, so the square. What's the key assumption you're making in that? What's the key thing that has to be? What's that thing? It's true. Well, what more fundamentally than that? Yeah. What is that? You say continuous, not continuous. That's also true. But all right. I'm looking for the word. Let me just go ahead and say it. All right. Independence, right? Independence. So when you're squaring constituent terms and using RSS, the core assumption that we're making is independence, right? One factor does not influence the other factor. Okay. So when we square one term, okay, we're saying that that term does not have a bearing on what happens with the other term. In vectors, that's true because of orthogonality, right? Orthogonality makes it so there's an independent limit, right? One is along one dimension, the other is along another dimension. They are perpendicular. Orthogonality makes it so they're independent, right? But I just think it's worthwhile again to put in perspective what we're doing in the class. Now that we're at the end, we want to put everything into perspective. Understand that this is actually pretty good reference that gets into a lot more detail on how you do uncertainty analysis. Now, one of the key things that you would do differently in a lot of situations is that you can't make the assumption that things are independent a lot of the time. All right, one factor might influence another factor. Okay, and so you have an entire section in this book that goes over an idea that's called covariance. Covariance, it means that the factors are not independent. Okay, one, you change one, it's going to impact another. You change the other one, it's going to impact multiple others. Things can be dependent on each other. All right, so one of the core things that we have assumed in all of our uncertainty analysis. Let me go ahead and write this on my paper here, so I'll go out and you guys to know. That core assumption for all of our uncertainty analysis when applying RSS is dependence. All right, so this is going to be true for multiple measurement uncertainty. All right, it's true on every level of our uncertainty calculation. Everything that we RSS or we square and take the root of, we're making the assumption of anything. And with multiple measurement uncertainty analysis, there are two factors on the uncertainty that we say are going to provide. One is random error, one is systematic error. And so we're going to have an understanding of a random error that's independent from our understanding of systematic error. What are we going to do at the end? The last step for multiple measurement uncertainty is going to combine those to form RSS. All right, so, but even before we get there, we're going to apply this kind of root sum of the squares multiple times. But every time that we apply it, we're making an assumption around independence. All right, we're saying that one factor is not related to the other factor. If you had a situation at your job where you couldn't make that assumption, what would you do? You crack open your reference, your text, or whatever the case may be, and this lays out multiple approaches where you can't make the assumption of independence. But from MechLAB2 to MechLAB2, we make that assumption every time. Okay? Because we're applying RSS, we're combining all these things. A core thing about each of these constituent parts, they're all independent. All right, so to review the equation that we put up last time, I'll show it to you guys in a couple different formulas. Let's go ahead and connect the dots with another concept that we touched on. Okay, here's in mathematical terms, so we got these up there last time. I think you guys have them in your notes, okay? To find out the understanding for the dependent variable, for the result, for the systematic error, what are we going to do? Each independent variable's systematic error, we're going to take it as a term, square it. Then take the square root of all the systematic error. Okay, that's just root sum of squares. For the random error, we're just going to have an understanding of each of the random error terms. And by the way, you'll see this if you have the text. In the example that we're doing today, we're going to use the action for the random error. We're going to use the standard deviation. On the mean. So each of the independent variables will have taken a set of measurements. We'll be able to find the standard deviation on the mean, and that is encapsulated in the random error for that independent variable. Okay, so we're going to use that for our each of the independent variables. We're going to take it, we'll take the root sum of squares for each independent variable. And then step 3, and once again, just to reiterate why we're doing so the key question here is why. We find an understanding of systematic error. We find an understanding of the random error. And these are for the output, the dependent variable. So we take the constituent parts, and we figure out what it is for the dependent variable, what the output is. And then, so then it makes sense that we can't just take the degree of freedom. All right, so each of the independent variables will have taken a set of measurements for. So if you guys remember the example, the simple example we used last time was relating things like this. We had an equation. But just as an example, we'll have a B term for the volume measurement that captures systematic error. We'll have a P term for the volume measurement that captures the random error. We'll have a B term for the time measurement that captures systematic error. We'll have a P term for the time measurement that captures the random error. And so we can measure each of these things different a number of times. So to get the standard deviation as an example for the volume measurement, we might measure the volume 15 times. We might measure the time 10 times. So when we're trying to figure out what the degree of freedom is for the result or the flow rate, The question becomes, is the degree of freedom 10? Is it 15? Is it something different? And the answer to that is, we're going to find a degree of freedom for the output, okay, for the flow rate in this case. All right, to find a degree of freedom for the dependent variable, you're going to apply this equation. And if you will notice, on the numerator here, the only difference we have between step 2 and this is in step 2 you're taking the square root, and in this equation you're squaring it. So to save yourself time, if you want to on an exam, right, it would make sense to find this and then take it to the fourth. You have the numerator immediately. All right, it's the same, basically the same equation. Common mistake that people make with this step 3 is they don't realize that each of these random error terms, you're taking it to the fourth before you sum it, and then this denominator here is not to the fourth. That's just the degree of freedom for each of the independent variables. So we take whatever the term is here for the random error, we take that only to the fourth, and we just divide it by, don't take the denominator to the fourth. That's just the degree of freedom for that independent variable. We're going to just sum up these results. You'll see that very clearly on the example that we're going to do. And then here's our last kind of step here, and this is what reflects our independence. So understand that we're taking the systematic error term, squaring it, and then plus an understanding of the random error. So all it is the student t-test value and the result from step 2. You square this one, you square that one, you take the root of both. That is a claim that systematic and random error are independent. All right, so we're going to get the result from that relationship. All right, so to connect some dots here, I want to show you guys, we have this slide on manipulation. I want to show you guys. This is the form of the equation that you guys will have on your equations. And these are reflecting error propagation. These are reflecting error propagation. So when do we apply error propagation? When do we apply when we apply error propagation? Yeah, it's a way for us to, when we apply error propagation, we take those partial derivatives again. We're going to get for each of those constituent parts, we do the RSS, we're going to have the units of the output. It's apples to apples comparison once we apply error propagation. Okay, so we're able to take in the equation we talked about last seconds. We did flow rate. And we know that we can't just RSS the volume at the time uncertainty, right? So we'll apply error propagation. So error propagation is also valid for multiple measurement. And it really is applied the exact same way. The exact same way. So if your units are matching, then you can just take, you can think of just, if I don't have any, let's say all the units for everything that I'm trying to find are voltages. Well, then just take theta to be 1 and it converges to the other equation. Take theta to be 1 in that case. All right. But if I have a problem with multiple measurement uncertainty where if you see the equation, and you know that these variables do not have the same units, then you immediately should think error propagation. And step 0 that you could even do in that case is you'll immediately jump into taking partial derivatives of this expression. Partial with respect to the volume, partial with respect to the time. You'll need those because you're tossing those into the table. All right? So error propagation, again, allows you to, when you do the RSS in each of these cases, allows you to compare apples to apples when your RSS with some of the squares. You're combining and units will be.
Okay. So we have, with our last example, we had one average value that we wrote in the this one is kind of like the text of averages that was coming.
So, and I'm glad you asked that because I want you guys to make sure that we know that I'm going to give you guys a table. All right, I'll give you in the table for each of the independent variables. I'll give you an average value. That's fine. I'll give you a p value. I'll even call it capital P. Okay, in the table, I'll say average values. I'll give you in the table. I'll give you capital P for each independent variable. I'll give you capital B for each independent variable. So your thought process here is dead on because you need the average values. So in this case, you need the average values. You know that partially with respect to Q. Let's do the easy one. Equals 1 over T. As we established last time, you need to throw in the average value used to evaluate. So that's why in the table, I'm going to give you the average value. You've got to plug those in to evaluate these questions. All right. Any other questions? Okay, let's have a look at this example. This is 520 in your reference book. That's why we're going to go through this in detail today. All right. 520 in your section 520. Now, the way that 520 is posed is more complicated than what I'm going to ask you guys to do on the exam. So notice this first step here. 520's problem statement, it gives you the standard deviations for each of these measurements. And the equation, I should probably copy that down here. So the equation of starting point is a stress equation. So the equation that relates all the variables is given in the problem statement as sigma equals PD over 2T. PD over 2T. And so what the problem statement says is we need to find the local measurement uncertainty for this stress sigma. So in order to do that, the problem statement gives us a standard deviation for the pressure, the diameter, and the thickness in this particular example. These are three independent variables, P, D, T. So this is given to us in the problem statement.
That 2T and delta T.
Given. This is given. This is not given. This is given in the problem statement. In addition to that, guys, we also need to know the number of measurements. Okay, because what do we need in this particular case? Standard deviation on the mean. So for each of these cases, we had to divide the standard deviation by the root of n. All right, it's just This idea that we don't just want standard, we already addressed this, right? We don't just want standard deviation. That's not helpful for us. What we want is standard deviation on the mean. Okay, so that's true here. It captures the random error for each of these independent variables. So I'm going to make it even easier for you guys on the exam. I will not actually ask you guys to even understand this relationship. I'm just going to give you a table where I give you, if you look here, 86.4 pounds per feet squared, 0.005 feet, and 0.00105 feet. Those are the p-values for each of these independent variables. I'll give you these guys in the table. Right, so you don't even need to understand that we need to calculate standard deviation on the mean. In the table that I provide you, I'll give you numerical values for these fees explicitly. Now, when we look at the table and we see these p-values, it's immediately clear to us that we have to apply error propagation. Right? How do we know that? Because these units are not the same. And we can't RSS this guy with that guy. So it's not good enough that these two are the same. All right? There's nothing we can do with that because this guy here is not the same. All right, so immediately light bulb should go off. You see different units. Immediate light bulb that says, okay, wow. Uncommon units, error propagation. And then this particular property statement, it says, all right, for the systematic error, all you have to do is take 1% of the reading, which we would interpret this as we would have to know the average values for each of these variables. So again, I will give you in the table average value for, and here they are listed for your notes. Average value for the pressure measure, average value for the diameter measure, and average value for the thickness measure. I'll give you these in that table. You'll know the average values up front. It's going to be clearly put in a nice table. So in that table, you'll know the value for the fees. You'll know the value for the average values. These are no. And even for the B values, I won't even ask you guys to do anything like take 1%. I'm going to toss you those also in the table. Toss you those also in the table. So this problem statement, if you look at the textbook, it says take 1% of the reading, also known as the average value. So in this particular example, B sub P would be equal to 86.1 pound per foot squared. B sub D, let's take 1% of that, that's going to be equal to 0.0058 G. And B sub T is going to be equal to, say 1%, that's at 0.00018 P. I'll give you these in the table. When we have to calculate, we have the table that gives you P values, V values, and average values. All right, so to do a multiple measurement uncertainty problem, this has to be known. This has to be known. This has to be known. These are all going to be in the table. And then what else needs to be known? You have to know what the relationship is between these different variables. So you have to know this equation. All right, in order to apply error propagation. Now, if just so happens that you get an example where all the units are the same, you don't necessarily need to know a relationship that shows you it's the same, right? But in any case like this, where we need to apply error propagation, we need to know how the independent variables relate to the dependent variables. We need to know that. All right. So that brings us into, we had our step by step here. Step one, find, it doesn't really matter what order, we're actually going to do step two first. Find the P for the overall system, find the B for the overall system, find a degree of freedom. All right, so even though in this note, it gives it to us in this form, we know that we have to apply error propagation. So we're going to toss in that partial derivative inside the square term. Because we have to apply error propagation, we don't have time in units. So that's why we see this on the step here. Here's theta sub P, here's theta sub D, here's theta sub T. And all we have to do is take those partials. Okay, so as I mentioned to you guys last week, I'm not going to toss you guys like a partial derivative. It's not a calculus class, all right? But I do expect you guys to know the power rule for partial derivatives. I don't think I need to provide that for you guys, all right? Y'all brush up on that if you're not solid on it. You understand why the partial of this equation here with respect to P ends up being D over 2T. You understand why the partial of this equation with respect to D is P over 2T. And you should understand why the partial of this guy with respect to T is negative PD over 2T squared. Just the power rule partial derivative. All right. So all we have to do, again, we have these values, the P's, these independent variables. So this is given to us. And this first term is talking about the P term we're going to square. We're going to take P sub P, this guy, 86.4. That guy there, multiply that by the partial derivative. We're going to ultimately square it. We're going to take the P sub D. So that's this guy. We're going to multiply it by the partial derivative with respect to D. We're going to square it. And then we take the P sub T, which is this guy. Toss it in here. We have our partial derivative. So this expression, how are we going to evaluate it? We're going to toss in, here are, once again, the average values of each of these variables. We just toss those in these places to evaluate. So for, as an example, here for P, we'll toss in 8,610 over 2, and for T, we'll toss in 0.018. Toss in the average value. And toss in everything we know, we end up with a value here for P sub theta. Why is P sub theta? P sub sigma. Why is it P sub sigma? P sub sigma because the result, the dependent variable is sigma. Okay, that's our notation. And we evaluate that at 7,275 pounds per foot squared. So we just want to make sure that our units here are going to make sense, all right? Because if we look on this guy, notice that we have P squared, all right? So we don't want these guys to be in inches, right? Because we know that when we, and if you're ever in doubt, units will never fail you. You can just plug these guys in and keep the units. Watch things cancel out. And you better end up with units pound per foot squared when you after you cancel the like. So when you evaluate this term. And here it's easy to see, right? Because we know that pressure is in pounds per feet squared. And we know that D and T are both linked. So those would cancel. So it makes sense that this guy ends up in the units of the output. Well, good question. So, just like always, guys, you guys have seen this in almost every class. The units will not fail you. So if you're in doubt or shaky, what are you going to do? You're just going to track your units and watch them cancel out so that they end up with the units. I didn't see who asked that. Hopefully that answered the question. You have a question?
Just to be clear, this is
Yeah, it's part of my, I gave you guys all my numbers.
yeah.
So y'all have it. Yeah, y'all have it.
So just a formula for the multiple measurement for VR, each of those is just combinations from one. So in this example, it's just one data set.
So, you look at the equation here. In the example that we just did, it is 3. It is 3. So it's a little bit, we like to use n for a lot of different things. But here, all we're talking about are the terms that are in the RxF. So it's 3 because if you go back here, you have 3 different variables. So that's why, look here, the n is talking about the number of terms in our RxF. We have a term for P, we have a term for D, we have a term for T. So, good clarifying question, I appreciate that. When we see this kind of mathematical representation of these equations, what we're talking about is we have to have systematic error term for each of the independent variables. So from 1 to n, right? And so in your notation, what we found is we're dropping the 1, 2, 3. So based on this, there's a B1, a B2, a B3. In the example that we're doing, this guy is B sub P, this guy is B sub T, and this guy is B sub T. So there was there's a little gap in notation of what we're doing. Hopefully that clarifies. That answer.
Yeah, so I guess my other question would be, when you say multiple, the difference between multiple measurement uncertainty and advanced level uncertainty and historical knowledge. So historical knowledge means you have, instead of just an output variable, you have multiple variables that you measure.
Yeah, so I'll give you that. Okay. You guys some kind of practical things to do for that. Okay. So since I've already established, I'm giving you a table that summarizes systematic, random, average values in one table. If you see that table, multi-measurement uncertainty. Okay? Because I'm giving you systematic and random errors and I'm summarizing the table. All right? In the other answer that if you in comparison to advanced and multiple measurement, all right, your standard deviation that you get when you're applying advanced level of uncertainty, the reason why we call it first measurement uncertainty. So it's literally like you just taken like 15 measurements with your system. The standard deviations that we're talking about really with the multiple measurement uncertainty with the p-values, they could be similar, all right, from a set of measurements in each independent variable. Or they also could be standard deviations that you know from a lot of experience, all right? The systematic errors in the system are almost always from a very in-depth experience. Okay. So what you asked is a good question. How would you know how to apply which one or the other? And the answer to that is multiple measurement uncertainty is the only approach we have that allows us to combine systematic and random errors. All right, and the understanding of the systematic errors would likely be from a very detailed understanding. And was that a direct answer? Okay. Other questions? I'll leave this one for you guys to verify on your own, but the process is the exact same, right? The only difference between this guy and what we do to get this one, the only difference in this example is here we toss in P sub B, and in this case we'll toss in B sub B. Here we toss in P sub D for this value. For this one, we'll toss in B sub D. For this one, we toss in P sub T for this term. And when we evaluate this number, we toss in B sub T. So the equation, as we've already seen, is the exact same. Okay, the only difference is RSS. All right, is of B's and not the P's. Okay, very similar. And then the partial derivative, if we're applying error propagation, that doesn't change. So if I'm new and I'm thinking about procedurally, what I'm doing on the exam, I would just do the partial derivative. I just evaluate those up first. I just take the partial derivatives, I plug in the average values, I get numbers for each of the things, the partial derivatives. And then I can just use those numbers and toss them in whenever I need it. That's an easy way, procedurally, think about how I solve. So hopefully that makes sense. So I would just, instead of writing this every time, I just find a numerical value for D over 2T. I find a numerical value for P over 2T. I find a numerical value for negative PD over 2T squared up front. Now, anytime I'm using the theta, I'm just tossing in the value. I don't have to rewrite it every time. All right, because when you guys take this exam, you're going to want to show every step. And I'll give you guys a ton of partial credit, but you don't want to be writing it necessarily too much of your time. All right. So step 1 result, step 2 result, we'll leave you to verify this on your own. And then here we have a step 3 equation, again, error propagation. Okay, so we can't drop error propagation. Okay. All right, this is the most common mistake that students make. So I want y'all to make a special note about this very common mistake. In this particular example, and I'll go ahead and write a note to yourself. I'll also provide for you guys in that table the number of times each of these guys were measured. I'll provide for you guys in that table I give you the number of times each one of the independent variables is measured. In this particular example, the number of n was 10 for all of them. So n, you can write n sub p was equal to 10, n sub d was equal to 10, and n sub t was equal to 10. So what does this mean? It means I measured the pressure 10 times, I measured the diameter 10 times, I measured the thickness 10 times. All right, I got the standard deviation. All right, and I use that n value to figure out what the standard deviation on the mean was. All right, but the most common mistake that students make is if we go down to this equation for the degree of freedom, if you look at what this equation is, it does not ask you for n. It asks you for the degree of freedom for each one of the independent variables. Without fail, about 20% of you guys are still going to here provide n. Don't forget n. Degree of freedom is n minus 1. And so let's first look to the denominator here since we're talking about this. If you notice on the denominator of this term, each of these guys, you have some numerator that's to the 4th, and it's divided by 9. Numerator is to the 4th, divided by 9. Numerator to the 4th, divided by n minus 1, 9. And if you look at the result from this process, actually, you end up with 10. But understand, guys, that this is a degree of freedom. So the key here is the degree of freedom for the overall system here is 1 higher than the degree of freedom for each of the parts. Okay, so it's not the same. Degree of freedom for each of these variables 9. The degree of freedom for the output is 10. Yes. So this equation here, so y'all get used to taking the square root of n because you need it for standard deviation on the mean. But in this equation, it's not standard deviation on the mean. It's just degree of freedom. You look here in the actual degree of freedom. Oh, okay. Oh, maybe my handwriting. I apologize. It's my handwriting. That's V.
Oh.
Square root of I would be.
Size is V sub I.
I don't know. This is not square root of I. This is V sub I.
So I will scratch that out. Make it look pretty. V sub I is
Any other questions, guys?
V sub R.
All right, so we're focused first on the denominator here. And all this is, and we're used to doing, in fact, we've already evaluated theta sub I. That's all this part of the equation is, right? This is just theta sub p, right? It's just the partial derivative evaluated. That's all this guy is. And then times the p sub p, 86.4. This is why I said that the whole process is redundant. Right? So we're doing very similar things multiple times. We evaluate the partial derivative, multiply it by p sub p. But the key thing, second most common mistake that people make is this denominator. You take this this result here, don't take it to the second, right? You take it to the fourth power out. And then this guy on the denominator of this term is not to the fourth. Divide that by 9. Now, would each of these guys need to have the same degree of freedom? No, right? You look at the problem statement. You might have this guy measure 10 times, this guy measure 15, this guy measure 20. All right, but in this example, we had each of these guys measure 10 times, so that's going to divide by 9. So same deal here. You just evaluate this partial and then multiply by a piece of p. We plug in for this partial and we multiply by a piece of t. All right, and keep that, take it to the fourth, degree of freedom. For the numerator, I would literally just take whatever this result is and take it to the fourth power. It's the easiest thing to do. But to show you what it looks like, all you're doing is the same exact thing, the same terms. You're squaring them in this case. And then you're summing them. And instead of taking the square root, you're taking it to the second power. All right, this is not a typo. This is the second power, no square. All right, you do this, multiply, evaluate that term, and you end up with 10. All right, this is another important thing I want you guys to have some notes. This does not end up being exactly 10. The degree of freedom for the system should be rounded up. So again, as an engineer, as you know, we want to be concerned. All right, so what we're going to do is we're going to take whatever the result is. We're going to go around that. the numerator, yeah, so P sigma, we can just take this and we can take it to the point. All right. So the last step we have here. We're going to evaluate this equation. B sigma. Oh, student t-test, piece P, 95. Right. And when we evaluate this, we grab 2,150. Plus 2.228. Just realized I made a mistake here, guys. It's correct. I'll get to it in a second. So we just evaluate this. You got your B sub theta, or sigma squared plus. This is from the table that we talked about. I'm going to go ahead and toss the table back up. All right, so what we had here was the degree of freedom of 10 and then 95, so that's where we got the 2.228. So that's why we grabbed that value from the table. The higher the degree of freedom we go, the smaller the value is. That's the mistake that I made when I talked to you guys about being conservative. So instead of rounding it up, okay, you're going to round it down to be more conservative. That's my mistake. So correct that for your notes. You want to be conservative. Then we would, if we had 9.01, we have to round it down. All right. So, but again, to evaluate things here, whatever the degree of freedom is, we find that on the table. We go over to the 95 column, and that's our 2.228 that we use. All right, when we evaluate this, we get 16,425 pounds per foot square.
And it's all wrapped up.
That is equal to this use of
164.
two questions about
It's square.
So remember, the result we get is degree of freedom. So I'm glad you asked that because the students make that mistake. So when you evaluate this expression, the result isn't it. The result is, it's degree of freedom already. So we don't have to do a minus one. We already have it. So we it doesn't calculate the 10. That's why when we go over to this table, the table is in terms of degree of freedom. That's why we add 10 here. Good question. Common mistake. Other questions? So when I say that the question will be very similar to this, it will almost be exactly the same in terms of the types of partial derivatives, right? It will be very similar in terms of, in fact, the process will be almost exactly the same. Actually, example 520. All right, I'll probably give you a slightly different equation. I've actually had Q equal V over T before on the exam. Same partial derivative. All right. So study 520. We spent a good amount of time on it. It's going to be very similar to what you guys see. Right. Any other last questions? Yes. Oh, okay. If it says submission, that's a artifact for a previous. Okay, so I appreciate you mentioning that. For the project planning, all you guys have to do is just go the ticket for the presentation validation. So just bring that sheet in, artifact. Remember what we said. Make sure you have that data set. And be ready to grab the measurement to verify that the measurement is set. So again, it wouldn't have to be exactly the same, right? But it should be in the same ballpark. And then the actually, I also had this question, so let me mention this again. Because you guys are setting up your measurement system, you don't have to attach your front panel block diagram to the project. You'll have the VI to be able to say, okay, here's the VI that we're doing. Yes. Not today. We'll get to that. Yeah, so it should be today. So that's what the deadline that Jay said was today. So I'll follow up with them. And if it's not today,
Let me terminate this broadcast.